Hello, Mr. and Mr. Ryan, are you
Yeah.
right? Good. Okay, so we have 5 more days to 700, okay? Okay, so we're given a positive integer, n, which is bigger or equal than 1, okay? And we want to find out, we want to return a list of binary strings. Binary, 0 and 1, right? A string which contains only 0 or 1. We want to return a list of binary strings. And for each string, what are these in common? Have you noticed? Yn equals 1, or 0, 1, this is easy to understand, but what yn equals 2, 0, 1, 1, 0, 1, 1. Binary. And there's one. Yes, but there's one thing missing, which is 0, 0. We don't want the string which contains 2 subsequent zeros. Okay, so for every substring of size 2, we don't want both zeros. We want at least 1 in any substring of size 2. So 0, 1, okay, here 1, 1, 0, here 1, 1, 1, at least 1. Okay, so let's take a look at example 3. 0, 1, 0, 0, 1, 1. What else? 1.
No, is that the combinations you can make?
1, 1.
No, is it the combinations you can make with the number of digits that n equals?
Yes. Look, n equals 3 meaning that all the strings in this list are size of 3, size of n.
I'm trying to find all the combinations.
Excluding the string which contains 2 consecutive zeros. Yeah? For example, this one, it doesn't have 0, 0, 1, right? Because look, this is...
With no consecutive zeros.
So, in other words, we need to have at least 1, 1 in any substring of size 2. Is this complete?
Yep. No.
I think so, right?
Yep. Yep.
Is it complete? Okay.
Yep.
So because this is not right, this is not right, and this is not right. So, okay, when n equals 3, how many combinations? Forgetting about the rules.
5.
N equals 8, yeah, because each digit we have 2 choice, right?
Yeah.
So it's 2 to the power of 3, so 8. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah? These 3 are excluded, okay? So these are the complete list. Okay, so any thoughts?
Just find all the combinations and remove the ones that have 2 zeros.
Well done, this is called proof of.
Yeah, but what are we finding out?
We want to return a list of the strings which doesn't have any 2 consecutive zero, or we want all the strings which has at least 1 for every substring of size 2, okay? So at least 1 for substring continuous, right? Of size 2, okay? So Ryan, you raised a very good solution, which is brute force. So, we know how to generate for each...
Brute force is always an option.
Yeah.
Yeah. In most cases, okay. I would say in 99% of the
Exactly.
cases. Okay, so brute force, because each digit only have 2 choice. So n digit is 2 to the power of n. We can generate this, right? And we check all these 2 to the power n solutions to check if any 2 digit is containing at least 1. In other words, if we found any 2 consecutive zeros, then this can't be included. So time complexity is 2 to the power of n. We need to times n, right? Because for each solution, we need to check. This is on, 2 to the power of n times n. This is the brute force time complexity. But do we have a better strategy instead of generating all of it? I give you a hint. If current digit is 1, what's the next digit?
1.
That's right, we can put 0, right? If we put 0, then that would violate the rule, okay? But if it's 1,
Violating.
but if it current digit is 1, how many choices we can put? If this digit is 1, what's the next?
2.
Yeah, we can put either 1 or we can put either 0, right? Simple. We follow this strategy. And how can we implement this? How many different ways can we implement this solution? Just this idea, right? We try we try placing the digit from the first digit, etc. With the first digit, we can put 0 and 1. And then the second digit, depending on the previous digit, if it's 1, we can put the 0 or 1. If it's 0, we can only put 1, right? So how can we implement this? What is this? I give you a few hints.
Window?
Not quite. So
Wait. Is it wait? Is it wait?
So no, okay, let me write the solution, and then there are a couple of ways of doing that, okay? And then you tell me what it is. There are a few choice, right? Remember,
It's like a time thing.
you know,
Like remember how before there was 11 hours in a 12-hour clock?
what is that?
Right. Remember the lesson how Dad thought that there was 11 hours in a 12-hour clock?
Oh yeah.
Yeah, that one.
Okay, so Ryan, you said true false, right? And then we can implement using recursion, right?
Desperately trying to change the subject.
Okay. Recursion, also we can say it's a depth first search, right? And then compared to depth first search, what's next?
Breadth of search.
Breadth first search, okay.
And then there's a union.
Union find, okay, that's different, okay. Okay, so let me write the recursion first, okay. Define recursion, right? Current digit, let's say current string is S, okay, and we know the n for sure, okay. We know the n here. If it is n is defined, okay, let's say n is defined. If the length of S is equal n, right? If we get this n digit, this is answer here. Answer at the beginning is the empty list. Then answer dot append S. We want to make a copy of S, okay? Then return. Otherwise, if the current string is empty, or the previous digit, the last digit of S is 1. Okay, so what does it mean? If we start with empty string, or the previous digit, if the previous digit is 1, so what can we get? What can we put? If the previous digit is 1 or is empty, then we can try with the 0 or 1, right? Yeah? So compared to 0, the next digit should be 1 only, right? So this is the case for the 1. We can try 0 and 1. Okay, so then let's try with 0 first. So 0, so S plus 0, right? Right, that's its next digit. We can try the digit, okay? And then, obviously we can do this, right? Okay, and else, if it's 1, if it's 0, then what happens? If it's 0, then we can only put 1, right? Recursion, okay? So look, these two branches have this in common. Okay? These two branches have this in common, putting the 1s, right? In both cases, we can put a 1. So in both cases, we can put a 1, then we can move this. Look, in both cases, if in this if condition, right? In both branches, we have this in common. So let's move this to here, and then let's remove this, okay? This is recursion or depth first search, right? Depth first search. It's kind of tree. We try with the empty string, okay? And then we can try putting the 0 here. We can try putting the 1 here. If it's 0, we can only put 1, right? If it's 1, we can put a 0 and 1, right? Okay, if it's 1, we can put the 0 and 1, okay? If it's 0, we can only put the 1. If it's 1, we can put the 1, 0, okay? So look, it's kind of like a binary tree, right? Binary tree. Each kid can spawn up to 2 kids, okay? Depth first search. This is S is the input is the string, okay? It's a string, and then we can improve the performance by converting to a list. If this is a list, right? If this is a list, at the beginning we put the empty list, okay? Empty list, and here instead we want to convert it to a string. So empty string dot join S. The list should be extended with the 0. List should be extended with 1 instead of the string concatenation. Look at this depth first search recursion. We look at the digit. We try to place the digit one by one. Okay. At the beginning, look, we have nothing, or empty string or empty list, right? If it's empty, we can put the 0 or 1. Alright, look at this. If it's 0, then we can only put 1. If it's 1, we can put 0 and 1. Okay, so we try to placing the digit one by one until we reach the string of size n. Right? And then otherwise we recursively check. It's just like we are iterating, we are walking through the binary tree. So for each digit, we have two choices, right?
On the tree.
If it's 0, it has only one kid. If it's 1, it has two
I
kids.
didn't say it was a bunch tree.
Okay.
I just said in that tree.
It's a binary tree, yes. Binary tree,
Yeah.
a maximum 2 kids, okay?
Yeah. How come there's 2 zeros?
Well done, this is mistake, okay? If it's 1, then this is 0, 1, okay? That's a test. Well done.
No, it's not a test. You just made a mistake.
Okay. Okay, so for each digit, we actually have two choices, right? In most cases, is we pick or not pick, right? Alright? Sometimes we pick both, sometimes we can only pick one. So the time complexity for this one is O 2 to the power of n, right? But compare to brute force. Brute force is we generate all these 2 to the power n and we check each one. This solution is 2 to the power of n, which is faster, okay? The space complexity, if we considering the output, then it's 2 to the power of n because each one has the size n, so this is 2 to the power of 2 times n, okay? If we don't consider the output as the space uses, then it's on. Yeah? So this is the first search. So next lesson we're going to talk about,
Forever search.
yes, and also there's another solution which doesn't require the,
Union.
no. It's another one, okay? So let's see for today, bye bye. Bye bye.
Bye bye.